Okay, we're going to continue with chapter 10. First, let's review this. This is a pre-calc thing. What is, do you guys remember the property of logarithms? Log is what?
Exponent.
Okay, yes, logarithms do equal exponents actually. But this is a times b. That's going to be the same as, remember, log of a plus log of b. Okay? The next one, so if when they're multiplied, it's addition. What do you think it is when it's divided by?
Subtracting.
Okay. Log of a minus log of b. Just a refresher here. And what do you do when there's an exponent right here? Do you guys remember what you do with that? Where does that little p go?
Oh, in the base.
No.
Wait, don't like logarithms equal exponents. Does that apply?
They do, but that's something different. What this is, this p goes out front.
Oh, okay.
Like that. Okay. All right. Here we go. Consider the following set of linear data. They already are telling you it's linear. There's no surprises here. Representing an account balance as a function of time. Basically, this is how many months that go by. This is how much money you have in your account. Describe the pattern of change. Change represents what in a linear equation?
Well,
Yep, it does represent the slope. So every time right here, how much are the x values going up by?
48.
Okay, so these are going up by 48 every time. Plus 48, plus 48 every time. All right? How much is the y changing?
By 480. Oh, so it's like. Yeah.
So the change is, when we talk about the slope, what? That's the change in y over the change in x. Those little triangles, that's the Greek delta. It means change.
So 10.
So it's going to be, yes, 480 over 48, which equals 10. If I ask you to describe the slope in context, meaning talk about what we've got here, what would you say about that 10? How would you describe that 10? What does that mean? Okay. Okay. So remember, it's the change in y over the change in x. So y is money, x is month. So this would mean every month our account increases by $10. Okay, that's how we would describe it. All right, the relationship between x and y is linear. If for equal increments of x, we have a fixed increment to y. Okay, so every equal increment, we have a fixed increment. So it's these are the same and those are the same each time. Okay, now we have non-linear data. All right? Describe the pattern of change. First of all, what does x go up by each time? Okay, that still is a 48. $48, $48, $48. Okay, but what happens with the y now?
Changes.
Yeah, it's not the same. Okay? First it goes up by what? 61.22, then it goes up by another amount, and so it's different.
92.71.
90. Okay? So it's non-linear. So for equal increments of x, we have we do not have a fixed increment by y, meaning y does not go up the same. Okay? In this particular case, this is actually an exponential growth because it goes up by a multiplier. So if I took this and divided by that, this divided by that, that divided by that, what would you get? So could someone on your calculator, could someone do, what is 161.22 divided by 100? Evan, will you do 259.93 divided by 161? Eli, will you do this one? Garrett, that one? Thomas, what'd you get?
The answer is 1.6128.
Okay, so when you did division, you got 1.6122. Evan, what'd you get? Same? You guys got the same? Okay. So when you have y2 divided by y1, or the second one, and you get the same number, okay, then it is exponential. Okay? All right. For linear data, we use the least squares regression to find the best fitting line. Okay? And we use it y equals a plus bx. That's just another way to write it. The slope is over here and the y-intercept, but it's our linear equation. For nonlinear data, the best fitting model would be an exponential regression. Okay, we can't use the least squared regression for nonlinear data because least squares regression depends upon correlation. Remember, that's the R, which only measures the strength of linear relationships. So what we do, and this is the whole big picture of what Chapter 10 is about, this is the solution. We transform the nonlinear data into linear data. We're going to manipulate it so it goes in a line and it's not curved. Then we use the least squares regression to determine the best fitting line or model for the transformed data. Finally, we do in this case, because we're talking specifically about exponential, in order to transform the nonlinear equation to model the original, we're going to use a logarithm. Because the whole idea is, and I'm going to remind you, and you guys kind of talked about it, that if I have log of base b of y equals x, okay, that this is the same thing. This is where we say the base is always the base. The base of x equals y. So if we come up with an exponential regression, we're going to transform it back to get what we're looking for by logarithms. We'll kind of get to that in a second. Okay, you got that? Okay. All right, so now the next part of what we want to do is we are going to linearize exponential functions. This is a bit of algebra that we're going to go through, okay? So I'm going to kind of go through it. So what you want to do is you want to write this exponential function like that, okay? So we have to somehow rewrite this to look like this. All right, so x and y are variables, and a and b, they're constants, okay? So right now I'm going to take you through kind of a method of how we're going to rearrange this to look like this, all right? Remember, a and b are just constants. So if I said that a equals log of 10, that's fine because it's a constant, okay? I'll write that down. Sorry, sorry about that. Didn't mean to have you write it down. All right, let's start with y equals a times b to the x. Okay, first thing you're going to do, take the log of both sides. because that's how we get the x out of the exponent, is take the logarithm of it. Log of y equals log of a times b to the x. Okay, in the very beginning of class, do you remember what's the rule when it's a times b? How can that be broken apart?
A minus B.
No, not minus, plus. So it's going to be log of a plus log of b to the x. Now, okay, we're doing all right. What was the rule about when the x is up here?
You put it on the other one.
That's right, we're going to put it in front. Oh, well, we did it, guys. Okay? I know, you're like, what? What is my slope?
X.
No?
Log.
Keep going.
B.
My slope is log of b, because it is this, remember, it's just a constant. It's a number. And that's my slope. What's my y-intercept?
Log.
Yep, you got it. Log of a. Good job, Evan. This is my y-intercept. It's a constant. All right? And do you remember, how do we write equations? What do we usually do when it's a predictor equation? What do I put over this part? A hat.
Sometimes yours is complicated.
Yeah, you. Okay, and that's the linear equation that goes right there. Okay, so now it says, so the graph of like xy is linear. This means the graph of x log of y is linear. Now, here's some conclusions. This is what we need to remember. If the graph of log of y is linear, then the graph of y is exponential. So if you're looking at a set of data and it curves up like this, okay, then in order to re-express the data, you need to take the logarithm of all the y values, and then it makes it linear. Does that make sense? Okay. Now, if the graph of y is exponential, then the graph of log of y is linear. Just the same thing, written a different way. Okay? Okay, what we are going to do now is we are going to actually take some data and we are going to do some practice, okay? All right, so we're going to take a little break right now.
Yes.
I know it's supposed to write D-R-A-K-E.
It's recording it.